This video is brought to you by Structural Central. Visit structuralcentral.com to quickly generate structural engineering calculations like those discussed here.
Hello engineers! Today I'm going to show you how to determine the reactions for a group of bolts that is eccentrically loaded. Eccentric loading of bolt groups comes up frequently in steel connection design. There are the obvious cases where the connections are being designed for moment, like for a bracket plate or for a hanger that has a lateral load. But also many shear connections for simply supported beams are required to consider eccentricity in their bolt groups. Eccentricity may be required for double angle, single plate, and T connections, as well as for shear splices. It's pretty clear that bolt group eccentricity plays an essential role in the design of steel connections, so you're going to want to understand how it works. Now let's get into it. Say you have a group of bolts that are working together to support a concentric load, which is when the load is being applied directly through the centroid of the group of bolts. Determining the reactions for each bolt is easy, since all the bolts support the load equally. Things get a lot more complicated though when eccentricity is introduced. Since the load no longer passes through the centroid, a torque or moment is being applied, which the bolts will also have to resist. This eccentric loading will result in reactions with different magnitudes and directions for each bolt depending on their location. There are two methods for determining the reactions in the bolts: the elastic method and the instantaneous center of rotation method. I'm going to show you how to do both methods. First, we'll start with the elastic method. The elastic method works by assuming the bolts behave linear elastically, which means that the force in the bolts is proportional to their deformation. This linear relationship makes it possible to use the principle of superposition to determine the bolt reactions. This allows you to split up the eccentric load into a concentric load and a concentrated moment. You can then determine the reactions for these loads using simple formulas and then add the reactions together. We're going to walk through how this is done. As we already mentioned, for a concentric load, the bolts support the load equally, so the reaction each bolt R is just the load P divided by the number of bolts N. The reaction will be in the opposite direction of the applied load so that equilibrium is reached. Now we'll move on to the concentrated moment. For this type of loading, the key principle is that the magnitude of the bolt reaction R is proportional to the distance from the centroid of the bolt C. This makes sense since the bolts will be rotating around the centroid, so the further a bolt is from the centroid, the more deformation it will see due to the rotation. The direction of each bolt's reaction will then be perpendicular to a line going from the centroid to each bolt. Equilibrium will be met when the moment from all of the bolt reactions is equal to the applied concentrated moment. Determining all of the reactions that satisfy these requirements may sound complicated, but the formulas are actually pretty straightforward. The reaction each bolt R is the concentrated moment M times the distance from the centroid C divided by the polar moment of inertia IP. Assuming that the bolts are all the same diameter, the polar moment of inertia for the bolt group IP is just the sum of the square of all of the distances from the centroid C. Since these reactions will need to be combined with the reactions from the concentric load, it will be useful to split up the reactions into their x and y components, so you can use these similar equations to determine each component of the reaction directly. Now that you have all the reactions from the concentric load and from the concentrated moment, you can just add the components together to determine the reactions at each bolt. Now we'll move on to the other method, which is the instantaneous center of rotation method. This method differs from the elastic method in that it takes into account the actual nonlinear behavior of the bolts. This allows the bolts to share the load more through load redistribution. This method is less conservative than the elastic method, but it is also considered to be more accurate. Determining the results, though, is much more challenging since it can only be solved iteratively. For this method, the bolts use the curved load deformation relationship that is shown on the graph. The formula for the curve can be found in AISC's Steel Construction Manual and is based on experimental results. The formula determines each bolt's reaction R by multiplying its ultimate reaction Ralt by this term, which will be some value between 0 and 1 depending on the deformation delta of the bolt. The formula is based on a delta max value of 0.34 inches for the failing bolt. The E you see in the formula is not a variable, it is the exponential function, so it is 2.718. The shape of the load deformation curve means that the bolts that have small deformations due to their location in the bolt group and still end up with significant reactions. For example, a bolt with a deformation of just 50% of delta max has a reaction that is 90% of its ultimate reaction. Since this method uses nonlinear equations, superposition is not permitted. This means you'll need to determine the bolt reactions that will result in equilibrium in the x direction, y direction, and in rotation all at the same time. The bolt reactions follow a similar principle as the elastic method loaded with a concentrated moment. The deformation in the bolts is proportional to the distance from the point of rotation. How it differs, though, is that the point of rotation, or instantaneous center, is not known. For the elastic method, the point of rotation is always at the centroid. For the instantaneous center of rotation method, the point of rotation can be located anywhere depending on how eccentric the applied load is. High eccentricities result in the instantaneous center being located close to the centroid, and low eccentricities result in the instantaneous center being located very far away. The process for finding the location of the instantaneous center requires doing many iterations. You start off by picking some location as your initial guess. The bolts that are the farthest away from the instantaneous center will be the bolts that reach their ultimate deformation first. These bolts will have a deformation delta of 0.34 inches, and the deformation of the other bolts will just be scaled from this value, so delta is equal to 0.34 inches times the distance from the instantaneous center to the bolt C divided by the distance from the instantaneous center to the furthest bolt C max. You then use this in the load deformation formula to get the force in each bolt. Next, you determine the x and y components of the reactions and the resulting moment about the instantaneous center using the formulas shown. You then add up all the forces to see if the bolt group reactions have the same ratio of moment and shear as the applied load. For our initial guess, the bolt group can support an ultimate load in the y direction of 11.1 kips. If this load was applied where our actual load is being applied, this would result in a moment about the instantaneous center of negative 89 inch kips. Since this is not opposite and equal to the moment from the bolt group reactions about the instantaneous center, our initial guess for the instantaneous center was not correct, so we must try again. It will take many guesses before you find the correct location. You'll need to determine which direction to move the instantaneous center, and then figure out how far to move it. This process requires many calculations, so it should be done using a spreadsheet where you can quickly guess new instantaneous center locations, or you can use software that is capable of finding the instantaneous center location for you automatically. Once the applied moment and the moment from the bolt group reactions result in equilibrium, the instantaneous center location guess is correct, and so the bolt reactions you calculated for that location will be the forces in the bolts when the ultimate load is applied. If you would like to easily create bolt group calculations like those discussed here, visit structuralcentral.com. There you will be able to quickly generate structural engineering calculations just by entering a few inputs. With its intuitive interface and live updating, you will be able to start getting results immediately. Enter the bolt group geometry directly on the drawing and see all of the bolt reactions right there. Provide the bolt size and the program will also determine the bolt group capacity and check its stress ratio. The calculations are well referenced with values plugged in, just like you would write by hand. You can also move the mouse over the variables to see a description of what they are and see all other instances where they're used, making calculation review a breeze. Head on over to structuralcentral.com and sign up for free today.